Hello and welcome. My name is Tim Gümnich, and together with Ludger Pehler, I'll be talking about Enzyme, a package for fast forward and reverse mode automatic differentiation. Enzyme is a compiler-based AD tool, which operates on LLVM-IR. It is thus language agnostic. This allows us to reuse one AD backend for multiple languages, instead of re-implementing automatic differentiation every time a new programming language is released. Unlike other AD tools, Enzyme can handle mutation and operate on mutable structs and arrays. Thanks to its compiler-based approach, Enzyme can also target GPUs and handle MPI and Julia threads. Here's a high-level overview of our compilation pipeline. We first lower high-level Julia code to LLVM-IR and perform a first round of optimizations. In the next step, we generate our gradients and run yet another round of optimizations. Finally, we generate our code. We will see in a later example why this first round of optimizations is crucial for Enzyme's performance. In this talk, I won't be going much into detail about reverse mode AD. For that, please see our previous talk at JuliaCon 2021. What makes Enzyme so fast? Enzyme runs on already optimized code and can make use of optimizations like loop-invariant code motion. Enzyme also makes heavy use of activity analysis to avoid computing unneeded gradients. It also makes use of an efficient caching algorithm. Differentiating after optimization can generate asymptotically faster gradients. Consider the function normalize on the right. It normalizes a vector by dividing each element by the vector norm. Note that the computation of the vector norm could be hoisted out of the loop. This is a common occurrence, and we expect the compiler to fix this for us. Running AD on unoptimized code makes the call to norm depend on the derivatives of the inputs, making loop-invariant code motion illegal. The derivative of our normalize function now runs in O of n squared. Running AD on already optimized code keeps the computation of the derivative of the norm outside of the loop, yielding a much better complexity of O of n. Activity analysis determines which instructions can impact the derivative computation. Enzyme avoids taking meaningless or unnecessary derivatives. This can, for example, be a call to CPU ID, or a parameter of a function which the user does not want to compute the gradient of. An instruction is active if and only if it can propagate derivatives to its return or a location in memory. Activity analysis is built on top of alias analysis and type analysis. A read-only function returning an integer, for example, is considered inactive, since it cannot propagate any adjoints to the return or a location in memory. For activity analysis to work, Enzyme requires activity annotations for all function arguments. Const is used to annotate arguments that do not participate in gradient computation. Active marks scalar or immutable values which we want to differentiate. Duplicated is used to pass structs and arrays with a shadow value. Duplicated no need is like duplicated, but does not compute the original value. Batch duplicated is used for batch mode. It works just like duplicated, but requires a tuple of shadow values. Batch duplicated no need, again, works just like duplicated no need, but takes a tuple of shadows. Caching is necessary in the case of reverse mode AD, for values inside the forward sweep that are no longer available inside the reverse sweep. This can be the case for values read from user input or values in memory that have been overwritten since. Enzyme can avoid caching in some cases by recomputing values. Enzyme also uses a min-cut approach to reduce cache size if it cannot recompute values and needs to cache. Consider the code snippet on the right. We iterate over the elements of two vectors, x and y, and sum up the elements. The sum is then further used in some function. At the end, we swap the elements of x and y, effectively overwriting them and making them unavailable inside the reverse sweep. A naive cache algorithm would cache all values for both x and y, and use them in the reverse sweep to rematerialize the sum. This leads to both unnecessary computations and allocations. The code on the right shows how a naive caching algorithm would look like inside the derivative of a function, with the allocations of the cache at the beginning and populating the cache in the first loop. In the reverse sweep, the sum is rematerialized from the cache before being used. Enzyme can approximate a smaller cache size by only caching the sum. Shown again in the code example on the right. The main difference here is that we can save one allocation of a vector and the addition when we rematerialize the sum in the loop inside the reverse sweep. Let's quickly talk about what's new in Enzyme in version 0.10. We introduced forward mode AD and batch mode for both forward and reverse mode. We also added a Jacobian operator to efficiently compute Jacobian vector and vector Jacobian products. Enzyme now also supports threads and MPI. Let's quickly recap the two main flavors of AD. First, forward mode, which evaluates the chain rule from right to left. Information flows in the same direction as the computation, so no caching is needed. Forward mode is most efficient for functions with much more outputs than inputs. Reverse mode evaluates the chain rule from left to right and requires caching, since gradient information flows in the reverse order through the program. It is most efficient for functions with much more inputs than outputs. Here is an example of forward mode AD. Forward mode AD makes use of so-called dual numbers. That means that for every value in our program, we keep another value containing the derivative. Let's walk through a quick example and differentiate the function f. I broke down the function into sub-expressions, w1 to w3, which we will apply the chain rule to. If we want to compute the derivative of f with respect to x, we start evaluating the chain rule from right to left by evaluating dw1 dx first. This is mirrored in the second function in our code example when we compute dw1. We then continue evaluating the chain rule until we reach the return value. Now, how does Enzyme compare to forward diff.jl? The new forward mode addresses many of the limitations of forward diff.jl. Enzyme can propagate derivative information through non-Julia code, like BLAS calls. It can also handle mutation on structs and arrays. And in general, Enzyme has better performance due to activity analysis. Batching in Enzyme enables us to compute derivatives with respect to n outputs in the case of reverse mode, or n inputs in the case of forward mode. Batching can also be applied to the original program outside of differentiation. Some of the benefits of batching are temporal and spatial locality in memory and better use of SIMD hardware. In addition to that, we only need to evaluate the function once. This allows us to cache values from the original function only one time for many evaluations of the gradients. Let us consider a function with 3 inputs. To get derivatives with respect to every input using forward mode, we need to run forward mode once for every input. For that, we need to mask out the arguments we don't care about by setting their derivatives to 0. Batch mode then lets us easily overlay those runs of our program. Batching in Enzyme makes use of the new activity annotations, batch duplicated and batch duplicated no need. The batch size needs to be known at compile time, though. On the right side is a short example of how one would use batch forward mode. Note how the shadow value of x is passed as a tuple, allowing us to know the batch size at compile time. It is also important to set the return type to batch duplicated or batch duplicated no need. The Jacobian operator in Enzyme has both a reverse and a forward mode variant. A Jacobian matrix contains all the first-order partial derivatives of a function. The forward mode variant of the Jacobian operator in Enzyme computes the vector Jacobian product, column-wise, meaning we multiply a vector with the Jacobian of our function. The reverse mode variant computes the Jacobian vector product row-wise, multiplying the Jacobian matrix with a vector. The chunk size needs to be known at compile time and can be modified by the last parameter of the Jacobian call. Batching reverse mode also requires Enzyme to know about the number of output parameters. The complexity of batch forward mode is O of the number of inputs divided by the batch size. For reverse mode, the complexity is O of the number of outputs divided by the batch size. Our example on the right computes the Jacobian vector product and vector Jacobian product of the function f and vector v. The vector Jacobian product can be computed by running forward mode twice or by running batch forward mode, highlighted here in blue. We set the shadow of v once to vx1 and once to vx2, effectively masking out one derivative each time. This is also called one-hot encoding. The Jacobian vector product is computed by running reverse mode 3 times, or batch reverse mode, highlighted here in pink, by seeding the derivative of the output vector of f differently each time. Using seed f1 to seed f3, we can determine the element of the output vector with respect to which we will compute the gradients from. And now I'll hand it over to Latke.
Hi everyone, my name is Latke Peter, and it's my pleasure to guide you through the second part of our presentation, which gets you somewhat more familiar with the parallel capabilities that Enzyme has started to provide to users. So let's say we have a scientific simulator which is highly parallel, such as, for example, let's say coming from CFD, a CFD simulator, where we have very large meshes to fully resolve all flow features. Let's say you have a safety critical application like a rocket. If you don't catch fine eddies and vortices, you might have something such as catastrophic failure. So you want to resolve to the finest scale possible, if possible, fully resolved simulations, which means you have a very large mesh, which you can't hold on a single CPU anymore, and documentational work just becomes way too large. So you have to scale to a complete supercomputer. But what has become a much larger topic in recent years also is NASA, for example, calls it VVUQ, verification, validation, uncertainty quantification. And a lot of these methods center around something like optimization, which can be either Bayesian optimization or gradient-based optimization in the larger sense, or, for example, uncertainty quantification. All of these require gradients, which in turn means that your automated differentiation engine needs to be able to differentiate for your entire code, which is why we've built that capability into Enzyme. The core here is that if you want to differentiate a very parallel program, then you want to preserve the parallelism of the program. And so basically you just want to, again, revert the direct acyclic graph, which, as I will show in the next slide, Enzyme is highly capable to do. The one special detail here that is worth mentioning also is that the way Enzyme implements parallelism models, it's able to combinatorially apply them. So for example, if you have a code which is quite common scientific computing, for example, which use, for example, MPI with OpenMP, which is called parallelism customarily, then Enzyme is able to easily combine the two without requiring a custom implementation. Or, if you're on the Julia side, let's say you have a program which is parallelized onto GPUs with CUDA.jl. CUDA programs are normally parallelized with MPI, and Enzyme is just able to do that, but in the case of CUDA with MPI, we haven't tested it yet, but in theory it works. So they can be combined combinatorially, which makes Enzyme quite unique in a sense if you compare to other implementations where you have to implement custom data types, for example, for MPI, OpenMP, and then they struggle to combine the two. So as Enzyme operates on the optimized compiler image representation, a lot of the parallel models look sort of similar for Enzyme. So let's say, for example, we look at the way threads in OpenMP parallelize, then the two parallelism models look exactly the same to Enzyme. The spawn sync parallelism that threads provides looks a little bit different, but that's mostly due to the unstructured nature. But again, it's just us reverting the DAG, so that's fine. MPI looks a little different, but we are really able to invert a control flow here, like a send becomes a receive becomes a send, and that way the communication flow can be inverted. So the message passing interface. So we are able to reverse MPI commutation for the most common MPI primitives. The way that works is that Enzyme.jl identifies the function call in its front end, which attaches the information and Enzyme's backend. So Enzyme proper and its MPI backend are then able to generate the corresponding derivatives without the information being lost through garbage collection in the lowering pipeline. Right now, we only implement a subset of the MPI standard, which is mostly due to the MPI standard containing hundreds of primitives, which require quite a large engineering effort to cover all of them. So if you, for example, use Enzyme on your parallel code and you run into an issue where you say, hey, this MPI call or this MPI primitive is not covered by Enzyme right now, please feel free to open a GitHub issue, and we will add that MPI primitive as quickly as possible. So what does it look like on level of code? Let's say you have some computational kernel, which inside of it contains some MPI communication. That for Enzyme is by now completely fine, so we can just fully reverse differentiate through the whole computational kernel, and the way you write your code is exactly the same as if it were a single-threaded function, and you just give that single-threaded function call to Enzyme. For Julia threads, we support the thread macro and also the spawn sync based on unstructured parallelism, and basically same story again, where the way the semantics for Enzyme work is exactly the same as if it were a single thread program. So you can just basically give those programs to Enzyme, make sure that your shadow is correct, and yeah. Looking at a little more practical example here. This is a reduced version of the MPI broadcast test from the MPI.jl repository. So if you were to say, hey, I want to apply Enzyme to it, how would we do it? So first, if you look at this code, then what we first need to do is we need to consider that we as Enzyme require the call to be wrapped in a function closure. So we first have to convert everything to a function closure, which you can then call per function. And then we can tag that function call with Enzyme for differentiation, which, glossing over some details with respect to the inputs here, then looks just like that for reverse differentiation. What's missing here, clear disclaimer, in this example is if we look at the function signature, then the function signature needs to have inputs with respect to which you want to differentiate, which is not shown here. If you say, hey, this is too simple, then we've got you covered. We did a rebuild of Lulash, which is a DOE proxy application by Lawrence Livermore, which by Lulash stands for Livermore Unstructured Lagrangian Explicit Shock Hydrodynamics Code, which is basically just Lagrangian hydrodynamics codes which simulate the shock. It's a reasonably big code base with 5,000 lines of code and 1,000 lines of code being allocated to its MPI communication. And Enzyme is able to differentiate through it. So if you're interested into that and want to see what that looks like in practice, please feel free to have a look at Lulash.jl. The URL is right there. And on the thread side, we've also differentiated through minibud.jl, which is a protein docking benchmark based on a larger protein docking engine, which is used in production, but not suitable for an HPC benchmark, and has the threads implementation, which is also able to be differentiated through, which is good for us and bodes well for further application and differentiation of thread structures. So to summarize, Enzyme is a tool performing reverse and forward automated differentiation. Enzyme.jl, more specifically for in Julia, it sets itself apart from something like Zygote, for example, by being also being able to handle mutable arrays and structs. And as Tim explained before, the way Enzyme is entangled deeply into the compilation pipeline means that it's extremely fast, and especially its LVM, like the LLVM optimization based or the Enzyme proper backend, enables a shared code base with other front ends. The new capabilities that we have added recently and we've essentially shown today are the forward differentiation, also including forward vector, support for parallel frameworks such as MPI and Julia threads. CUDA.m already existed. We are now able to automatically vectorize with the batching primitives that extends not only to batching automatic differentiation call, but also if you're not automatic differentiation, we can also batch that function. And we've exposed an API to compute a Jacobian and also products thereof, such as the vector Jacobian product or Jacobian vector products. So everything in Enzyme is fully open source. So we have the Enzyme.jl repository with the full source code in there of Enzyme.jl, and also there exists the Enzyme proper repository as well. There exists a compiler Explorer instance, which would highly encourage everyone who's really interested in the way that Enzyme works to have a look at, where you can basically just write a bit of C code, for example, and you can really see how the compiler changes that and go through compilation steps. Right now, Enzyme is an LLVM incubator project, so there's a topic on the LLVM discourse, as well as a topic on the LLVM Discord. If you're interested or want to get in touch with problems, please feel free to have a look there. And also there exists an Enzyme channel on the JuliaCon Slack channel, where we will always respond as quickly as possible. And if you have any further questions or are really interested now, please feel free to join our weekly meetings every Tuesday at 1 p.m. Eastern Time. Thank you very much for your attention and have a great day.